Alrighty, so I kind of looked at my previous answer and yeah, it was end up being backtracking. I'm going to try to explain it. So the setup is going to be you want to use the information from the board to identify what are the filled values at each spot. So for each row and column and box, sub box of the overall board, let's say you initially have false for when not a particular value is already found in that box. So initially, let's say everything is false if it's all blank. If there's a 5, 3, and 7 in that row, in the first row, then I'll set the 5, 3, and 7 indices to be true for row 0. Similarly, for subbox 0, I'll set 5, 3, 6, 9, 8 indices to be true. 0 index, so -1 from that, but anyways. And then as I go through and initialize kind of the board information, or get the board information for each spot and then translate it to true values for the appropriate row, column, box. Here there's a function box RC to convert from the row column indices to the sub box index. But so I set those to true. I also will create a queue of tuples of the row and column positions for where I need to fill in the blanks are, where the blanks are. And that's going to be necessary because that's going to be the process or ordering by which I go through the blanks, and I need to know like the particular ordering in order to kind of do the backtrack algorithm. Additionally, I sort the blanks, the blank tuples, by kind of least information to most information, or sorry, most information to least information. So basically the the positions where there's a lot of information about a particular cell, so like a lot of information about the row, column, and sub box about it. So maybe like this position is sorted going to be the kind of first thing I backtrack, first position I kind of attempt to fill in. And once I have that, I go backtrack 0. Backtrack 0 calls the backtracking out function. Here, your basic backtrack function will have this a recursive function, and it'll have some counter or something to indicate that it has finished backtracking. So if the index ever reaches k, where k is the number of blanks, then it's going to know that it's solved the board. Initially index is 0, and then as you call the backtrack later on, it'll be index +1 if it works. So in general, backtracking is going to require that I go through the positions and evaluate possibilities, every possibility at that position, and if it can work, then it goes on to the next position. So for instance, I use the blanks queue and the index into that queue. So I take the position of a particular blank, then for every value in the set of values that can be there, which is 0 through 9 or 0 through 8, however you want to think about it, 1 through 9, 0 through 8. As long as it's not currently a value that is already assigned to that row, column, and sub box, then I kind of initialize the value to that spot, or set it to be assigned to that row, column, and sub box, set the board to be that value, and then backtrack one step further. If this returns true, then that means that everything's worked all the way to the end, and I return whatever the current state is. Otherwise, you kind of reset to a previous kind of erase that value setting. So make the board back to the blank, remove this value from the things that have been removed from the row, column, and subbox, and then it loops to the next iteration, and then it goes to the next value. And then if all those values don't work, then it returns false. That means that at some point it will backtrack to a position where there are other values that it can go through. So yeah, this is a good refresher on backtracking methods. I think what I mainly forgot was how to create this ordering of positions by which I iterate through the backtracking algorithm with. That was I think that'd be the spot that I need to refresh myself most on. It's like in a very general setting like this, where you can iterate through like all those cells and rows and columns and every other way, creating a particular way by which you know what positions you're at to guess, and then how to guess it, right? But this is probably the thing that was most unclear to me when I was trying it. Anyways, so summary, this is going to be a backtracking algorithm. So first, create data structures to keep track of what values are available for rows, columns, and boxes. And this basically ends up using 2D array of booleans for 2D. The 2D array actually, it's an array. End up using it. Yeah, 2D array of booleans. For each, and then iterate over initial board and set values based on that. Set values in part 1 based on that. Additionally, have I guess I used have an array or queue to track what positions have blanks, which will be used later in backtracking order. This is optional. I'm pretty sure this optional. Sort the queue, backtrack array with blanks that have the most information to be at the front. This will this speeds up the process of finding the correct value for while guessing over the possibilities at each spot. And then 4, create a backtrack function, which is a recursive function that takes an index into a queue of blanks, get the current blank from Q, iterate over all possible values. For each, try to fill in the blank with that value, modifying the structures from part 1 appropriately, and then recursively call backtrack of index +1. If that returns true, then it's good and return. Otherwise, reset the state to prior to assignment of value. If all values are not possible, return false. Then 5, call backtrack with 0, and that should do the rest. Okay, so there's other ways of maybe setting this up. You could make it recursively decrement the counter, where the counter starts with the number of blanks. Maybe it's maybe the Q is backwards, or in that case, but and then when the counter reaches 0, then return true. Something like that. Time complexity. This can be. Ooh, what is this? Time complexity. This can be O of O of the number squared. So the number of backtrack calls should be up to the number of blanks, or the stack of it should be up to the number of blanks, and then each backtrack call has maybe 9 subcalls. I think it might be n squared. No, that's too. That seems to be too fast. Each backtrack call 9 factorial 9 to the power of n squared. There's 9 possibilities for each spot. There's 9 possibilities for each spot. And then the number of calls could be 9 times 9 times 9 times 9 times. Shucks. So in the board there's 81. 9 to the power of 81. That seems like a huge number. Yeah. There's no way that's right. Okay, rather than give an incorrect answer, I'm just going to say what's definitely correct is I don't know. I don't know for sure. I think it's higher than polynomial, like n squared, but less than exponential. It's almost certainly less. So I think it might be some form of factorial. Like, because the number of possibilities should reduce each time. So maybe like 81 factorial is still too big. Yeah, that's even bigger than 9 to the power of 81. Yeah, I'd have to actually research it in order to know for sure. Base complexity is going to be O of 1 for the, well, O of n squared, where n equals 9 for 9 size Sudoku. I misspelled that. Since the 2D arrays need to track the usage of each value. All right, not terribly satisfying, but it is what it is. And the actual runtime was, I think, like 90-ish%